sparse today. You dedicated few that want the review. That was poetic. Well, it rhymed. Yeah, Glenn. Yeah. I'm going to start with some announcements first. One, it's on the schedule, it's on the university's calendar, it's on our syllabus, it's right here. Anyway, but you know how it is. Everybody forgets when the final is. So there you go. Things to note. It is here, it's right here. It's during our class time, but a little different. So a little earlier. It will be comprehensive. I plan on making 60 questions, so it'll be twice as long as a normal one. But it's all the same format. Just like the homework, the clicker questions, the pre-lectures, and the exams have all been drawn from the same pool all semester. So are these. You're still allowed a calculator, one cheat sheet, whatever you want on there. Just might have to cram more into it, right? Because it's everything. There won't be the opportunity for a retake on the final, though, because that's the end. So, no retake. You guys think any other questions or concerns about the logistics of the final? Okay. Second, some of you have noticed that the Center for Teaching and Learning Excellence sends out surveys to the students about the course and about me. And bottom line, I don't see these until after I turn in your grades, but they're anonymous anyway. I don't know who said what. So, but these are important to me. I like these, so I am encouraging you to fill them out. Although I think now, correct me if I'm wrong, do they force you to have to fill this out before they let you see your grade? That's what I was thinking. But, it's mostly, on a scale, strongly agree, strongly disagree, or is he good, 5, bad, 1, that type of stuff. So you can whip right through it without thinking. But there are opportunities to write something out. And I read every single one of those and take them to heart and make notes for next semester or next time I teach this. So I encourage constructive criticism, good or bad, about the course or me. You have a while to do this, but last formal chance in class to encourage you to do so. Number 3, I've announced, I think 3 times now, there are still 6 unassigned clicker device ID numbers. They're the same ones that have been posted on WebAssign in the announcements section and that I've sent in a couple emails. Now I've looked at those. Those people are still showing up periodically, or at least they're still participating periodically. So I know they're still coming to class, getting answers, but I haven't heard from them. Point is, if that's one of them, you should go look and see. If that's you, you're not going to get any credit for anything you did all semester until I know who you are. I have the results, I just don't know who to give them to. So if you haven't and you're worried, check the WebAssign under the announcements section to see if that's one of your ID numbers. If so, just contact me. I have your papers that I finished grading. So at the end of class, they're sorted by last name, mostly, into here. And I still, it's one of those where I enjoy this assignment. I enjoyed reading them. This was fun. It's just, it's long. I admit that, but I did it. Last time I think I didn't finish until the final. So, here they are. The rubrics are attached. So I wrote the scores there and comments throughout. So hopefully you can understand or see why I gave you the grade I did. I just posted them on WebAssign too, so you can at least see the score. But here's the comments. The average was, I just updated scores as much as I could for the class. The class average, if everybody aces the final, the class average will be a B. Then I put it in. If everybody gets the highest F, flunks the final, the class average is still a C. So I think that's pretty good. So I'm confusing the averages. I think the paper average was high C. No. Now I forgot. It was a high C or low B. It gives you an idea. There were several that got 100 outright. So I was quite pleased. Some were really well written. Most, the large majority of them, my purpose for doing it, having you explain some physics, I feel successful about. So, am I done with announcements? Yes. So, do you have some specific exam questions you're thinking about? I looked at the retake right before class started, so some people could have done a slightly more. And the average of the retake was a high A, so these people figured out the answers. But, iridescent colors. It's just for later reference for those of you that have this on. So that is the thin film interference section in chapter 29. Superposition and interference, which we covered a lot. And then it goes single color thin film interference, where we talked about bubbles. I showed a soap bubble thin film. I showed a picture about gasoline on water. So these were thin films where the light goes in. It can comes in, and some of it can reflect, some of it refracts. Some of that then refracts, some of that reflects, some of that reflects, some of that refracts. You get it all. Point is, if your eyeball's over here, then this ray, when it gets here, the one that goes in it and bounces back out, has a slightly different path length than this one. And so these two could be in or out of phase depending on how many wavelengths fit in here. And so a thin film can constructively or destructively interfere certain wavelengths and colors. So a soap bubble, for instance, you see those colors? It's caused by the interference of these waves. Same with gasoline on water. Same for pretty much all iridescence you see. That was one example of a shell. There's a thin coating on it, and you see cool iridescent colors on it. Those are created because white light's coming in, because we see most things in white light, and some colors were getting subtracted out or filtered and destructively interfering. The ones that do constructively interfere and make it out, we're combining to make the iridescent colors. Yeah, that was long-winded, but you need to know why. Yes, it's caused by interference. Yeah. Yep. Yeah. Other questions you guys had about anything? The whole semester, your entire life up till this point. No, let's see. I went through one that ones that people didn't do as well on. The source of a sonic boom. That question was: A, must itself be an emitter of sound, or it isn't, or it could be, or it couldn't be. So what creates a sonic boom? Let's just think back to that. Pressure building up. So yeah, it's a superposition of pressure waves. What caused those waves? A moving object. And how does it have to be moving? Yeah, at least as fast or faster to create a sonic boom. Right. So that object that's moving fast as or faster than the waves themselves, does that have to emit a sound on its own? Or it never can, or it could if it wants to, was the question. does the source of that sound, or the sonic boom, those waves that superimpose, have to emit sound itself? Well, I saw what your answers are, but I was just, what are you thinking now after the retake in a weekend? And it may or may not is the correct answer. Example, a jet airplane. It just whizzing through the air. It doesn't give off sound on its own. The engines can, but just the fact that it's going through creates a pressure wave. It's going as fast or faster than the speed of sound. So it creates those pressure waves. A boat in the water. As it goes through the water, it pushes it. If it goes faster than the speed of sound in water, faster than those waves can travel in water, you get a bow wave. And you probably, if any of you have gone jet skiing or something, and one of those hit you, and you're like, whoa! That's the equivalent of a sonic boom, but in water. But it's not because the boat makes sound, it's because it's making pressure waves in the medium. Hopefully that helps with that one. I think there was another one people weren't quite as groovy on. Oh, here's one. The majority still got it right, but it was a high majority or minority that didn't. Consider light energy that is momentarily absorbed in glass and then re-emitted. So first of all, is glass transparent or opaque? Transparent to visible light. What's it opaque to? Ultraviolet and infrared. That's true. Most glass. There's always exceptions in different types. So glass is transparent. Okay, so light comes in and it's momentarily absorbed by the glass because it has to get through it. That's me doing the wave comes in, bloop, and then bloop. It puts the photon back through and its neighbor catches it and so on. Compared to the absorbed light, how does the frequency of the re-emitted light compare? It's the same. That's the answer to that one. The majority got it, but a lot didn't. Think of it this way. This red jacket over there, sweatshirt, it's red. It's being absorbed by the glass and re-emitted through it and comes out this side. It's still red. It still has the same wavelength. It's still the same frequency because it's red. It doesn't change colors magically because it goes through glass. So the light that comes in has the same frequency and wavelength when it comes out of glass. It's not the same light, technically speaking. The photons that enter this side are not the same photons that come out this side because they got absorbed and re-emitted. But they have the same frequency. Yeah, if this glass is colored now, then let's say it's blue glass. Let's say this is blue. I look at things. Most things look now blue. So it still doesn't change the blue light that gets through it. But it filters some other wavelengths from getting through. So it absorbs those. But it doesn't change their frequency. And while we're on that, in that case, blue glasses, red gets absorbed. So the frequency of red, how does that compare to the natural frequency of that blue pigment in the glass? We got a higher and vibrates with it. Somebody break the tie. When do things get absorbed? When they resonate. Good, Kira. So it's with it. So the red wavelengths, red frequency, matches the natural frequency of that dye, that blue dye, and so it absorbs it. Because at resonance, for little energy, you get a lot of motion, and that gets dissipated into heat, so that the energy of that red light goes away, converted to something else, and so it doesn't get through. That's why it gets absorbed. So things that get absorbed are resonating. Hence, back to these glasses. Infrared light is absorbed by the molecular vibrations. They like to vibrate at that, so it absorbs infrared and it doesn't get through. Ultraviolet makes the electrons resonate, and that absorbs those. They don't get through. Visible light is at a different frequency, so it doesn't resonate with these, And so not as much energy is dissipated, and it can still get through. It made me think of another question. I just forgot it. Oh, well. Other questions? Well, I figured if you do, just raise your hand, that you probably have forgotten more of the first stuff, right, than the last stuff. So I was hoping you had more questions. It'd be more particular to you. I have a potential bank of questions. I just took them. I go, I like that one. I like that one. I like that. And I haven't decided yet, but here's what's going to be the final. So I can walk through that, and it can remind me of stuff. Having said that, I think your best study methods are go back and make sure you've hit the main topics in the book and remember them. With each of the chapters, the headings are at the end with the review. Definitions and things. I mean, you need to know what things are called. Way back, do you remember facts and theories? Hypothesis, what that stuff is? Nodes from our last exam. If you don't remember what some of these things are, that might not do as well. Also, I think going back to your homework, pre-lecture, and exams, review. Do you understand why those are all the correct answers? Look at my answer keys. I have explanations to each of those. Because if you can't understand those, you probably won't be able to apply the same knowledge just to a new question. Because they're the same style and type, just could be completely different question. Or maybe I'll just take some from the past assignments. But I think that's the best way. And you have all my videos too if you need me to hear me explain something again. They're all there on YouTube. All right, let's see. What's inertia? Whole semester. We don't.
Property of matter.
It is a property of matter. Hey, good job. It resists a change in motion. It's a property of matter. It's directly related to mass, how much somebody's mass has. So if you double its mass, you double its inertia. You double its resistance to change its motion. And what exactly do we mean by motion? What is it trying to change? Excuse me. State of, and what'd you say? Direction could be part of it, actually. State of what? What state? What kind of motion? What type of motion are we talking about? Is this velocity, acceleration? Velocity, just to specify. Yeah, it's because in the normal world we just say motion, but in physics, does that mean acceleration or does that mean velocity? What's the difference between those two? Right. We had speed and we have velocity. Velocity is a vector because that direction is important. We had lots of things that were vectors, so the direction matters. So, what were some other vectors where direction mattered? Acceleration is a vector. Good. It matters which way you're trying to accelerate. Absolutely. Force, which way you push on something, whether you push to the up or down, left or right. It's coming back, right?
Potential and kinetic energy be vectors?
Potential and kinetic energy. No. No, those are not. Speed, though, is a scalar. It just has magnitude. So velocity is speed with a direction. It's a change in position with time. That's how you're changing your position with time. Thus, direction is a way to change your motion. So inertia tries to, resistance to changing motion, velocity, it tries to resist changing direction as well. Acceleration is a change in what?
Increases time.
Change in velocity. It's how that changes. So if you're not changing your velocity, you're not accelerating. So you can be moving, remember this? But not accelerating. It gets confusing, you know, when we toss balls up in the air. Okay, what's the acceleration of this piece of chalk on its way up? Bless you. Yes. On its way up, the acceleration is due to gravity. It's 9.8 meters per second squared, or about 10. We used a lot. And which direction is that? Yeah, down. It's accelerating down. But it's moving up. That's just like slamming on the brakes in your car, right? You're moving this way. You slam on the brakes. You don't automatically just start moving that way. Actually, you don't move that way at all. But you accelerate that way. And that decreases your velocity. It changes your velocity from going 100 miles an hour to 0 miles an hour. How about on the way down? What's the acceleration? Good, it's the same. So now it increases your velocity down. All right at the top, when it stops, right, momentarily it doesn't go any higher, and it's not going lower. It's vertically, it seems to stop for a brief instant. Instantaneous velocity is 0 right there. The vertical velocity is 0 at that moment. What's its acceleration? It's still 9.8 meters per second squared, because it's still being accelerated down. That's what made it stop.
He just decided to stop working right then.
Yeah, if you turned off gravity right here, what would happen? Let's say it's like, normally it'd be like this. Let's say right at that moment we turned off gravity. Describe its motion. What would happen to it?
Whichever direction it was last going, you go that way.
Good. I'm glad you said it wouldn't just stop right there. Yeah, it would head off that way. With whatever horizontal velocity it had at that point. Which would be whatever horizontal velocity it got shot with. You know, let's say it gets shot initially with this velocity. Remember, if you break it into components, there's our x and y axes. Two-dimensional motion. The y component of this velocity is drop a perpendicular, and it's this much. Drop a perpendicular to the x, and the x is that much. So that's the horizontal velocity, that's the vertical velocity. Those are the components of this if it's shot over at an angle. Does this change throughout the trip? Why, Glenn?
Acceleration acting on it in the opposite direction.
So it's accelerating this way?
Well, the horizontal is going to stay the same. The vertical is going to change.
Right. The horizontal stays the same. Is there any acceleration in the horizontal direction? So with two-dimensional problems, remember you have to treat them as two separate one-dimensional problems. Horizontally, there's no acceleration. There's no forces. So there's nothing to change this. If the acceleration in the x, there's no change. So it just maintains. Right here, it's v sub x. Right here, it's v sub x. Right here, it's v sub x. If you turn off gravity, it's v sub x over here. If air resistance is significant, and you have to worry about in the problem, then that could slow it down a little. But without air resistance, no. The vertical velocity, though, goes from this, gets smaller and smaller and smaller to 0, and then gets bigger and bigger in the opposite direction. And by the time it gets back here, it's the same magnitude, but opposite direction when it lands. You remember in this? So let's see, if you had, I think we had a problem, or at least I have in the past, an airplane's cruising along and it drops a package. Okay, coming along, and I drop a package right at this point. Where will it land? Who thinks A? Who thinks B? Who thinks C? So and then I drop it right there.
How fast is the plane going?
I didn't tell you how fast it's going.
It's going as fast as
Just talk to me. What do you think? Does anybody think it'll land today?
No.
Oh, good. Then we see you've learned something this semester. Here, ready? Oh, it was over here. Because this has the same horizontal velocity as the plane. So as soon as I let go of it, it still has that horizontal velocity. If I go faster, yeah, it'll go further. So yeah, it could be B or C. It's a trick question. I just wanted you to talk to me. But it's definitely not A. Because both things are going on. So that's inertia, resistance to motion, which really means a change in velocity. So any problem, if there's no net force, there's no net acceleration, there's no change in velocity, it just keeps going at whatever velocity it was at, whether that's at rest, 0, or 55 miles an hour, you know. It can maintain whatever velocity it was currently at. It just won't change. That throws people off. It did some of you at the beginning. Wait, there's no net force on me. But there's forces pushing me. Like the car. When you go 55 miles down the highway, 70 miles an hour. What am I thinking? 70 miles an hour. What's making you go forward? The velocity is 70 miles an hour. What force is making you go that far, that fast? Yeah, the car. The engine turns over, it makes the wheels turn. The wheels are actually pushing on the ground. They're trying to rotate. But that force is on the ground, so the car is actually trying to make the ground move. Newton's third law says, equal and opposite. The ground pushes back with this exact same force. So it's the ground that actually propels you forward. But yeah, it's because the engine is working and expelling energy. Trying to turn the wheels to push them against the ground. Ground pushes back on the car. It's the force on the car. So we got a force this way. Ground on car. All right. If that's all we had, then from Newton's second law, or as I prefer, this way, we know it's going to accelerate based on its mass. But that means the velocity is going to change. And it'll just go faster and faster and faster and faster. This would be changing. What if you're maintaining 70 miles an hour? What else is going on? Inertia. Talk to me about inertia. That's a resistance to wanting to change. Yeah, it's in motion, so it wants to stay in motion. So this obviously got it moving. We accelerated up to 70, but now we're staying constant at 70. So yeah, if we turned off the car, would it stay going 70?
well, without friction, yeah.
Friction, yeah. And now what did you say earlier? Something, yeah, must be pushing on it back the other way. You guys know if you turned the car off, it would eventually come to a stop. Newton's first law of inertia says, well, like Glenn said, it should just keep going at 70 miles an hour unless acted upon by another force. So there must be some other force trying to accelerate it in the other direction. And yeah, that's usually friction, air resistance. If those are equal, and when we sum up the forces, let's add them all up. This is in the x direction. We don't have to worry about y. So we have F1, F2. F1's going in one direction, plus negative F2 because it's going the other way, or just minus. That's going to give you the net force on the car. If they're equal, the net force is 0. What's the net acceleration? 0. So even though two things are pushing on the car, it doesn't accelerate because they're in balance. Mechanical equilibrium, do you remember that term? And if that's 0, it doesn't change velocity. And its inertia just keeps it going at 70. Mechanical equilibrium, a lot of people think, oh, it's static, it's just sitting there. No, it's when the net force is 0. There's no net acceleration. It's not changing its velocity. It could still be moving and be in mechanical equilibrium. So we balanced forces. Let's balance the vertical forces in this case. What are they? That'll help you remember them. What's the vertical forces on the car?
We could argue what little gravity the mass of the car exerts on the Earth. It's nothing.
That's true. The Earth pulls on the car.
And the car pulls up.
Right, so we have Earth on car. The pair, the action-reaction pair of that is equal and opposite of the car pulls back on the Earth. It's trying to accelerate it up. That's the pair. But notice, again, that's on the Earth. If we're looking at the motion of the car, we just want the forces on the car. But that's the pair. Good. Why doesn't it fall down? It's trying to accelerate down, right? What do we call it that's holding it up? Yeah, the normal force. Normal, or we've called it both, support. That's the ground on the car. The action-reaction pair is the car pushes on the ground. But that's on the ground. So the two on the car are these two. And yeah, if it's not moving vertically, there's no acceleration vertically. These are equal. But again, see how we separated the vertical from the horizontal in two-dimensional motion. Again, if you think of questions, just raise your hand. Oh, we have this one. What if you're standing on 2 bathroom scales? What will they read? Half your weight. What if I go like this? What will this one read? Yeah, all my weight. All my weight. Half my weight. What about now? Right, this one will read more than that one. Or like this one will read more than that one. But what's the total reading got to be? My total weight. That's the Sharon of Forces because you're distributing it. I kind of like it up here. Is this all coming back to you? Could you calculate these things? I might have some simple ones. If you knew that 2 of these values, can you get the third? For example, I'm 100. Oh, why do I always not get that? I think I'm about 70 kilograms. We'll go with that. Who cares? If my mass is 70 kilograms, how much do I weigh? What's the force of Earth pulling down on me? Well, let's see. M is F over A. We got that. We want the force. So my mass is, if a mass is 70 kilograms, and it's being accelerated at, we'll use 10 meters per second squared, multiplied, then you get 700 newtons. Kilogram meter per second squared is a newton. That's my weight. I'm 700 newtons. In English terms, that's about 160 pounds, if I'm converting right in my head. So a 70 kilogram person is being pulled down with 700 newtons of force. If I'm holding onto a tree and I'm not sliding down, how much does friction have to be? Less, equal, or more than 700? Equal, because the up is balancing the down. So there must be 700 newtons of force of friction between me and the tree. If I loosen up my grip and make that less friction, then there's a net force down of something less than 700. And yeah, I start sliding. It's no fun. How about with these? Do you have a change in position or whatnot? We did a lot of dropping. Let's do that one. If I drop this, if it starts with 0 velocity, after 1 second, how fast will it be going? Good job, Casey. Do you remember that, or did you recalculate it? Because we did it a lot. I'm just curious. You reasoned it through then. If the acceleration due to gravity is 10 meters per second squared every second, that's the change in velocity. If you started at 0 and you went for 1 second, that's going to change your velocity 10 meters per second. So after 1 second, you're now going 10 meters per second. Did everybody follow that? After 2 seconds? 20, 3, 30. Yeah. What if you already started going 70 meters per second? If you started at 70. In other words, let's say you shot something down at 70 meters per second. How fast will it be going 1 second later? 80, because it's going to change by that much. How far will it have fallen? Not this one. Let's start at 0 again in 1 second. That's correct. The y distance will be 5 meters. And we had that formula 1/2 AT squared. It guides our thinking. But that comes about from the reasoning that, what if you start at 0 meters per second and you end up at 10 meters per second, what's the average velocity? 5 throughout the trip is the average. So on average, if you went 5 meters a second for 1 second, you just covered 5 meters. Now during that second, you start at 10, and what are you going to end up at? 20. What's the average? 15. So for that second, how far do you go? 15 meters. 15 more meters. You've already gone 5. So you'd be now 20 meters down. Or you can just plug into this and it works. You can time something, remember? 1001, 1002, 1003, splash. Put in 3, you know the rate it accelerated. That tells you how much it changed. You know exactly how far it dropped. Oh, gotta remind that. All right. Heavy object and a light object. You drop them. Who hits the ground first? Same time. Why? They accelerate the same? Then why does everybody outside of physics class, including half of you before we started this class, thought the heavy one goes faster? What do people miss that you guys now know? The force of gravity is the same? On both of them. So if I have something heavy and something light, is the force of gravity the same on these two? Force. What does this one weigh compared to this one? More. That's the force. Weight's a force. So this one's heavier. The force of gravity is greater on this one than this one. Do you see that now? And that's why people think, well, this one's got a greater force, so it should hit the ground first. It's being pulled with more force. That's absolutely true. But they hit the ground at the same time. I'm not going to drop my laptop. And that is because they accelerate at the same rate. But they definitely have different forces. Why does it take more force to accelerate this at the same rate as this? Why? Here's your clue. Because if your mass is bigger, your force has to be bigger. If the mass is bigger, you have more inertia. It wants to resist that change in velocity. So you have to pull on it with more force. The heavier things are feeling more force to achieve the same acceleration, which all objects have. This was all neglecting air resistance, obviously. Does that make sense? So that's why. The forces are different, but the accelerations are the same. Well, what else? Terminal velocity, that's the balance of an upward air resistance, balancing weight. Once it's equal, you no longer fall any faster. You don't accelerate. Remember that? Terminal velocity. Potential and kinetic energies and transferring energies. You can look those up. Remind yourself, the potential energy was based on position. Kinetic energy was based on time, velocity. And energy is always conserved. A lot of your papers were on this. You're all over that. That and Newton's third law you guys are great at. Those are the two most common. But it can transform. You raise something up, it has this much potential energy. If it loses all of its potential energy and now it's moving because it fell, you know exactly how fast it could be moving. Because this energy that it started with has to equal the energy it ends with. Or somewhere in the middle, like a roller coaster, halfway up and down. It has a combination of the two. And it's work that we did to transfer energy from one thing to another. Work was force times distance. Some force had to apply to this thing to try to move it. Gravity, in this case. Up the roller coaster, you do work, you pull on it up a certain height, expend energy to get it up, and now it has this much energy. You let it go. Gravity pulls on it. It goes down, this decreases, but now this increases. It's moving faster, and the ride's fun. Yay! Remember, it's not how fast you go that people like at amusement parks. On an airplane, you're going fast. Is that exciting? No, turbulence is, because what's it trying to do? It's when you go around corners and loop-de-loops and you accelerate, trying to change your velocity, overcome your inertia that we really feel it, and that's when people get sick or excited. And we had collisions, momentum and impulse stuff. Momentum, mass times velocity, inertia in motion. If we change that momentum, usually it's by changing the velocity than the mass, but you could do either. In order to do that, it takes a force for a certain amount of time. You apply a force for a certain amount of time, and that will change an object's momentum because it makes it accelerate. So it's either going faster or slower. Like the egg into the wall. The wall exerts a force on it for a certain amount of time. It does work on it. It smushes the egg for a certain distance. What's that? Where's that energy go? It was in kinetic. It now converted into deformation and heat, sound. And it changed its momentum. It was going this fast. Now it's going zero because it stopped. We have a change in momentum. What else do we call all this? I heard somebody whisper it. Be brave. Impulse. Yeah. Change in momentum is the same as impulse. So Newton's third law, you have a collision. You guys know that little Timmy on his tricycle and the big Mack diesel truck, they hit. They both feel the exact same force. But Timmy gets hurt more because he has less mass, less inertia. So he's accelerated more, but it's the same force. They also feel the same change in momentum if they come to a stop. Because they were both going fast, they both stop. It's the same change in momentum. Because they feel the same force for the same collision. So they receive the same impulse also. Timmy still is worse for the wear because less mass. So I'm probably going to have one on here of a collision. You know, if you have a this mass going this fast and it runs into this mass going this fast or at rest. The total momentum before, what's this guy's momentum? What's this guy's momentum? You got the total. That has to be the same after the collision. So if they bounce off each other and this one starts going back that way and this one that way, you can figure out how fast they're going based on their masses. Or if they stick together, they're both moving together at the same speed. But you just figure out the total momentum before, the total momentum after. There were some examples on the homework and the test, so you can review that. Energy. We got all these energies. Power. We did that a few times. That's energy per time. The rate at which we use energy. So if you push on something for a certain distance, you do work on it, you're changing its form of energy. But how fast did you do it? You can figure out the power. Or if you drop something from a certain height and it falls yay far, and it happened in 2 seconds, well, you just changed all this energy in 2 seconds. You know the power that something did it on. Or running upstairs or whatever. And this is any type of energy. Electrical, potential, kinetic, work. Well, we're running out of time. You guys got any other questions? Projectile motion, two-dimensional stuff, forces, balance. I figured this was the most rusty. But then there's all fluids. Remember density and buoyancy, Archimedes principle. Yeah, Stephen?
What are the, pulleys, wheels?
Oh, the simple machines.
Yeah, what are those?
The simple machines are, because I write too slow. They're listed in your book, but yeah, we have wedges, inclined planes, screw, wheel and axle, pulley. Help me out if you remember one I haven't said yet. Lever, thank you. And they all can do what? They're good for what? Simple machines. Force and distance, good. They deal with those things. They can multiply one or the other, or reduce. So say you can't lift that refrigerator up into the moving truck, right? It takes too much force, more than I can exert, because its weight's too big. Can't lift it. I'm hosed. Well, come in, inclined plane. Now instead of going from here to here, I got a ramp. The ramp changes the direction. I don't have to overcome all of its weight, just a component of it. So I can exert less force to push it up. That I can do. But because energy is conserved, I have to push it a much larger distance than if I just went straight. So you can't multiply energy with a simple machine. It's not magic. But you can make life easier or move something further than you move over here. So it's kind of like the work on one side has to balance the work on another on a simple machine. Good. Other questions? If you think of some, contact me. We can work through, if something doesn't make sense and you look at my solutions and exam stuff. I'll have you can come down and get your papers and we'll call it good. I won't see you for over a week.